Hello everybody, this is an unusual video format for me in that I'm going to try to recreate in real time a what they call site reduction tables, which is really important in celestial navigation when you're out on the open water and you just have a sextant and you have a nautical almanac, and you'll need site reduction tables to figure things out for you. So this is all done before the age of computers. And we'll see if I can duplicate it. And I want to say I've gotten a lot of information and a lot of inspiration from this YouTube channel called the Nav Station. Andy Howe has a really amazing course. He really goes through. I don't know how many episodes there are, but it looks like there's 12 episodes in this course, and how to use a sextant, and not only that, but how to actually perform celestial navigation. So actually the table that he referred to in the video was different than the one that I'm going to use, but let me just show you what I've got going on here. So 10 days ago, I came up with this idea that I wanted you guys to challenge me to just duplicate one page. And actually what ends up happening is I will duplicate all the pages. But I wanted you to pick a number, V, P, and C, not knowing that V was volume and P was page and C was column. And so Ruhif picked 5, 117, and then 8. And so I'm going to go with volume 5, page 117, and column 8. So I've already opened that up here in another window. So let me scroll down. Here's page 117, and this is volume. What did I just say? Volume 5, which has pretty high latitudes, and he said column 8, which is actually 67 degrees. So I'm going to focus in on this far right-hand column. Now, unfortunately, this is an odd-numbered page, a right-hand page, which means that that it's latitude contrary to declination, and then the bottom of it has a completely different local hour angle. And the latitude's the same. So this column is very complicated. You'll see there's this line, and I'll explain what that line means. So what I'm going to do is I'm going to back up a page. I'm going to go to page 116, and I'm going to first try to duplicate this 67-degree column. Now, what these three columns are is a calculated elevation angle of the body in question. In other words, what you would see through your sextant is the elevation angle observed, H sub O, and so H sub C is elevation angle calculated. D is useful for interpolation, because we're only going to the nearest degree of latitude and the nearest degree of local hour angle. So you're going to need D to kind of interpolate between the values. That's called little d. And then Z is your azimuth. So HC is in degrees, minutes, and tenths, and then little d is in minutes and tenths, and then Z is in degrees and tenths. And then down the right-hand side we have declination. So let's switch over to my little piece of paper. And so what I'm going to do is I'm going to actually start with a blank spreadsheet. Well, I might as well do that now. I'm going to start off with a blank spreadsheet. So I'm going to do a new blank spreadsheet. And I'm actually making this in a shared folder. I'll share you guys the link a little bit later. So I've got a blank spreadsheet, and I've got a blank sheet of paper. And let's jump in. In fact, I'm going to do the timer. I'm going to start the timer now, and we will see how I do time-wise. All right. So one of the things that you want to think about is we're living here at a house, and there is a celestial sphere above our heads. Got to move my microphone over. There's a celestial sphere above our heads, and let's say we're in the northern hemisphere. So we have the north celestial pole, and well, that runs down through our position. Well, up in the sky, we're going to have the celestial equator. celestial equator. Now, of course, if we look north towards Polaris, we'll see the sky rotating around it. But if we also look south, we'll see stars that are south of the celestial equator, such as the lower half of Orion's body, Orion being the wintertime constellation. So his hips, the 3 stars of his belt, that rides on the equator, the celestial equator. And so what we're going to focus on is, well, first off, I need right directly above our heads is our zenith position. So what we're going to take a look at is the relationships between our zenith position, the celestial equator, our visible equator, or our visible horizon, we should say. This is our celestial horizon. And then how these things relate to each other, specifically with the star, or the body in question. It isn't necessarily a star; it could be the moon or the sun or a planet. Now let's put latitude on here as well. So if Polaris were directly above our heads, we would be standing at the North Pole. So as the celestial equator comes up, this is actually our latitude. All right, this is our latitude. And so what we're going to find is there are various things that add up to 90 degrees. For example, latitude plus colatitude equals 90 degrees. That's how you get to our zenith. So that's the first diagram we want to take a look at. And the second diagram is actually I'm going to draw the celestial sphere, and I'm just going to plot a couple points. Now, obviously, we're not a house sitting on the ocean, so let's make it a ship. But the celestial sphere, we're going to just make it a sphere, and I'm going to draw the celestial equator. Celestial equator. And then we're going to draw the north celestial pole. All right. Now, what we're going to have is and let me just use red again. We're going to have what if you're sailing, it's what they call the assumed position. So it isn't necessarily your dead reckoning position. You're going to make some sort of assumption as to where you are, but then you're going to be sighting in your sextant to a body, something that's in the sky. I'm just going to draw it as an asterisk, but it could be the sun, it could be a planet, it could be a star. So in this case, we are looking to our east. I made a mistake here. If this is the celestial equator, if this is celestial sphere, this is not our assumed position. This is actually our zenith. And then this is the actual body in question. And we can actually start making, drawing lines. So you can draw a line to the north celestial pole, and then there's going to be this other component. And we can also draw a line down to the body, and then down to the celestial equator. But we're actually sighting in with our sextant. So you're actually going to have in fact, I'm going to pick a slightly different color so it can show up a little better. You're going to have a celestial horizon. Celestial horizon. And so when we're sighting in this body, it's going to be a certain amount. This is going to be our elevation. And that's going to be H sub O for our observation. And we're going to actually change that to H sub C for calculated. But what we end up having is a triangle, a spherical triangle. So let's redraw this triangle. And this time we're not going to do all the details. So I've got this side of the triangle. So here's our star. And then this is the extra part. So if that's the body, then this is going to be the declination of the body. Because again, this is how far the body is above the celestial equator. So the declination, and we're going to get that value from the Nautical Almanac if we were performing celestial navigation. And then here we have our zenith position. And our zenith position, we if we're actually on the oceans, we're going to estimate what our actual latitude is. So this part is actually latitude. And then we've got the sighting to the body, and then this is actually our H sub O, and this is to the celestial horizon. Now, there are a couple things that we know. First off, we know our latitude, or at least we know the latitude of the assumed position. So we can figure out this one, which we are going to label I'm just going to label it CoLat. C-O-L-A-T. So because latitude plus CoLat equals 90 degrees. Because again, where did we get this? We got it from the celestial equator to the north celestial pole, which is a 90 degree difference. Next, in purple, we've got our declination. Our declination, which is how far the body is above the celestial equator or below, and we're going to talk about that, same versus contrary. So if that's the declination, then this purple line is going to be called CoDec, co-declination, because the CoDec plus dec is also 90 degrees. They are both measured between the celestial pole and the celestial equator. Now, the other thing is we don't know this distance here in green, and that's actually going to be the distance to the geographic position of the body, or the GP of the body. So that is actually going to give us our distance in nautical miles if we convert that 60 nautical miles per degree. We'll get to that in a moment. But we want to focus in on our sextant reading. And so that's going to be over here, our H sub O. But I'm going to actually take the complement of that. So I'm just going to say 90 minus H sub O. That's going to be the green. Now, what do we actually know in terms of angles? Well, now Andy Howe, he always talks about the local hour angle. It starts from where we are. So local hour angle. Basically, if you draw a line around the pole, and if you always go westward, so this is actually the LHA, or the local hour angle. But for purposes of the spreadsheet, we're actually going to be measuring this thing in here, which technically is called T, but mathematically it works out the same way. And the reason why that is that if our position were over on this side, if we were taking a western sighting instead of an eastern sighting, if our position was over here, then we would just draw a perfectly complementary triangle over here, and in which case the angle, the local hour angle, would be this acute angle in here. All right, so I'm going to treat this angle as local hour angle, even though technically the local hour angle is going westward towards the body in question. All right. So essentially, we have three pieces of information. We have, since we know our latitude for our assumed position, we know CoLat. Since we know the declination from the Nautical Almanac of the body in question, we know CoDec, and we know the local hour angle. Again, that's using the Nautical Almanac plus our assumed position's longitude. So we know three pieces of information. We know a side and an angle and a side of a spherical triangle. Okay, so what we're going to use is the spherical law of cosines to figure this out. So the spherical law of cosines, if you have, I guess I should probably label these sides. What color haven't I used yet? All right, so I'm just going to label this A, and we'll do this one B, rhymes with Z, also C. And then CoDec is actually going to be little a. CoLat is going to be little c. And then 90 minus our observed altitude is going to be, what did I just do? I was supposed to write a B here. This is little a. All right. So the little letters are the arcs, and the large letters are the angles. And we essentially know angle A and then arc C and arc B. Now, the interesting thing about the spherical law of cosines, or spherical law of sines, is everything is in terms of angles or arcs. All right, so the spherical law of sines goes like this. Cosine of A, or actually, yeah, cosine of A, that's the little a, is equal to cosine of B times cosine of C, plus the sine of B times the sine of C times the cosine of angle A. All right. So what we're going to do is we're going to translate this in a little bit into the how we're going to find our missing side here, because we know it's two sides. But what we'll do until then is we will jump into our spreadsheet and we'll start working on our spreadsheet. But hopefully I've gotten everybody too confused. But I do want to say that essentially what the site reduction table will do is it basically solves a spherical triangle for us in table form, because obviously this was before the age of computers and calculators, and of course, trigonometry, especially inverse trig, would be really, really difficult to do on the high seas. So they solved all possible triangles and then put the results in table form. All right, so let's jump into our spreadsheet. And I just want to have a couple starting positions. One of the things that is always good in terms of programming is, instead of putting in like a hard coding in a constant, let's take a look at what we're actually going to be doing. We're going to be putting in 67 degrees because that's what Ruhif had selected. We're also going to be using our local hour angle of 57 degrees. So local hour angle 57. Latitude of 67 degrees, and instead of programming those in like inside the code, it's good practice to actually define those so that we can change them later. So I'm going to call these things starting points. Starting points. And our first starting point is going to be LHA, and I'm just going to put a little indicator 0 to 90 because we're going to cover all the other local hour angles as well. And we're also going to have latitude. Latitude. Now, I'm going to highlight these two cells green. And usually when I'm doing these spreadsheets, these types of spreadsheets, I like to highlight in green the stuff that the user is allowed to change. So we're going to start off with an LHA of 57. I think that was 57. Yeah, LHA of 57, and then a latitude of 67 degrees. All right, and that's going to be our starting point. Now, all the formulas that are used in the spreadsheets they don't use degrees. They do everything with radians. So what we're going to do is we're going to have to convert stuff to radians. And so we're going to get the radians of our LHA. Okay, and not only that, but we're going to call this LHA. We're actually going to be able to put that right in our formulas. So that's one of the nice features about some spreadsheets is that, if I've named the cell LHA, I can actually type in the letters LHA into a formula, and I don't have to remember that it was cell E2, because E2, who knows what E2 is. I'm going to do the same thing with latitude, but remember, we don't want the actual latitude as the length of our side. Going back to my drawing, latitude, we want CoAlt. So I'm going to have to subtract from 90, but I also want it in radians. So equals radians, and then I'm going to do 90 minus my latitude. Okay, and then like we did with LHA, we're going to actually name the cell. We're going to name this CoAlt. All right, for colatitude. And again, we'll be able to actually use that right in our formulas. So now I'm just going to do some cosmetic stuff. There's something called same and contrary. We're going to get into that in a little bit, but basically same means that if we're in the northern hemisphere and we're looking at a body that has a positive declination or a northerly declination, we're in the northern hemisphere, the body is north of the celestial equator, we call that same. Because the same tables could be used south of the equator. If you were south of the equator and the body was south of the equator, like for example the Southern Cross or Alpha Centauri, then that would also be same as well. All right, so now here we're going to put in a nice cosmetic version of our LHA. We're going to just kind of type in a little formula here. So we're going to have LHA colon space, and the ampersand just sort of concatenates text. So ampersand, and then I'm going to do I'm going to use dollar signs, $B, $2, because I want an absolute cell reference. I'm actually going to be copying this formula another place, so I want an absolute cell reference. So when I copy the formula, it doesn't shift everything over. We need a comma and then a space. So we're going to have the one LHA, and we also want the local hour angle that is sort of 360 degrees away from that. So going back to the drawing, it's basically one of these is the actual LHA and the other one is actually angle T. But as you're going to find, both of them will give you the same triangle. All right. So in my spreadsheet, I want to have another ampersand, and then we're going to do 360 minus that actual typed in LHA. So that would be $B, $2. Okay. And I want this to be really big because it's at the top of the table. So just like on the actual things that I'm trying to duplicate, it puts that in real big letters. And so I want to kind of duplicate, that onto our table. Now there's a bunch of columns that we're going to need. Regarding the actual table, we have declination runs down the side, and declination goes between 0 and 90. And then we have h sub c, which is the elevation calculated, and then little d, which is the differential or the delta, and then z, which is going to be related to our azimuth. So I'm going to have those columns as well. Where's my spreadsheet? Okay, so I'm going to have, dec. I'll do capital DEC. Declination. We'll do h sub c. We'll do little d. And we'll do capital Z for azimuth. Now, our declination was going to go from 0 to 90. And there's a little trick. If you type in the first few numbers, then you can do a sort of a fill down by dragging the cells. I'm in Google Sheets. So I'm going to drag this down to about, I think it's about 99 or 100. It's 99. Yeah, well, we're going to go down to 91, and I'm going to explain that in a little bit. Now, because that's kind of a pain to kind of drag all that way, what I'm going to do is, just for cosmetic purposes, I'm going to actually hide most of this spreadsheet by collapsing it down. And this is going to allow me to do fill down commands. When you do fill down, you click and you drag. And then so this will allow me to do fill down but I could see the full spreadsheet right here. It also would be nice if I put in the cells for the other calculations. So going back to my drawing, so we've got CoAlt, we've got CoDec, we've got LHA, but I need a couple of these other ones. Now I did label this 90 minus HO. I didn't realize that I actually also labeled that CoAlt. So I'm going to put CoAlt there as well. So my declination, which is 0 to 90, I'm going to need to find the CoDec, and I'm going to use lowercase b for that. So B, which we'll label CoDec. And again, this is just going to be a calculation. It's not going to be shown because it's obviously not in the final table. I need my CoAlt, or 90 minus my elevation. So that's going to be lowercase a. That's the green side on that triangle. And we'll call this CoAlt. I'm going to be able to use those to find ultimately h sub c. So I'm going to do h sub c, but I'm going to do in decimal. Because if you go back to the table, h sub c is formatted in degrees, minutes, and tenths. Degrees, minutes, and tenths. And that's a very, very specific way of formatting, and I'm going to need to do something with the spreadsheet. So I'm actually going to calculate that in decimal form first. All right. And what else do I want? I want the delta, or the little d, also in decimal. Okay, I think I'm ready to actually start putting in code for this. So again, we how do we solve this? Well, first off, we're going to need to take the declination and change it to CoDec. So again, it has to be in radians. So it's going to be 90 minus declination. You can just click on that. All right. And I'm not going to do autofill because I'm going to be doing a lot of fill down repeatedly. But what we're going to do now is we're going to go and we're going to have to find our CoAlt. So going back to the drawing, this line in green, that's the CoAlt. So I need to be able to solve for that. So that's A. All right, that's CoAlt. So how am I going to solve this? I'm going to need to take the inverse cosine. So A is going to be, or arc cosine, right? Arc cosine of this entire thing. And now what we're going to do is we're going to translate that using the letters A, B, and C. So B, every time we see B, that's actually CoDec. I should probably do this in another color. Every time we see lowercase b, that's CoDec. All right. So, and that's there and there. Every time we see lowercase c, that's CoAlt. All right, there and there. And then capital letter A, that's actually our LHA. All right. So our CoDec, what spreadsheet, where is that located in the spreadsheet? That's going to be E8. All right, E8. So I'm going to just say this is E8, and then our CoAlt. Our CoAlt, we actually labeled CoAlt, so we just used that straight. And then LHA, we actually named that as well. So we're basically going to find the arc cosine of the cosine of E8 times the cosine of CoAlt plus the sine of E8 times the sine of CoAlt times the cosine of LHA. All right. So we're going to type all that into this formula. So it's the equals ACOS is the arc cosine, and we're going to have the cosine of E8, which is CoDec, times the cosine of CoAlt. All right. See how I just typed that in there? And we're going to add this to the sine of E8 times the sine of CoAlt times the cosine of LHA. Okay. And I need to finish my formula for arc cosine. Okay. Now that's probably not very exciting, the CoAlt, but we're actually going to convert that from radians back to degrees, and we're going to get our h sub c, or the actual calculated elevation angle, and we're going to compare that to our sextant reading. So this is going to be h sub c. This is our first pass at h sub c. Again, this is the calculated elevation angle. So we're going to do, and we're going to subtract this from 90 because it's but we have to convert it back to degrees. All right, so 90 minus degrees, and then that was F8, right? CoAlt was F8. All right, so we have 12.2 degrees or 12.28 degrees, and let's just take a look at the table. So, and again, we're going to go back to the table. What we're looking for is 12 degrees and maybe 20 some, or no, 0.28. That would be 12 degrees shy of 15 minutes or so. So again, I want to do same name. All right, 12 degrees 17 minutes. Do you guys see that? 12 degrees 17 minutes. So, and that's at 0 degrees declination. I'm getting all excited because it's always nice when the stuff works out. Okay. Now the decimal is going to be comparing this h sub c to the next one. So you guys know that deltas are always later minus initial. So we're going to say equals. We're going to click here, even though G9 doesn't have a formula yet, we're going to be filling down pretty soon, and then we're going to subtract the initial value. So G9 minus G8. And of course, that's now a negative, but as soon as we start filling down, this is all going to make sense. Okay? Now, this decimal h sub c is pretty ugly, so we need to do something with that, and we have to format it. And one way of dealing with that is it's 12.28 degrees, but we need to sort of chop off the 12, right? So this is called truncate. So we're going to say 12.28, we're just going to chop off the decimal, and that's a truncation command. And this is in cell, G8. So cell h sub c, which is really one of the most important table entries. So we're going to use the truncate command, and we're going to truncate G8, right? And then I'm going to use the ampersand. I'm going to add the degree sign. All right, just to make it look nice. And then we're going to, once you take the truncated, once you truncate the decimal, well, we got to bring the decimal back. So now we're going to truncate it again, but we're going to subtract that from the original version, the decimal version. So we're going to say G8 minus trunc G8, right? So we're going to take the original value and we're going to subtract the truncated value. And what this is going to give us is, I forgot the ampersand here. This is going to give us just the decimal, but I don't want the decimal. I want this to be converted into minutes. So we have to multiply this times 60. All right. Now let's just take a look at what that looks like, and something went horribly wrong. So, and did I do G8 minus trunc G8? I forgot to put this in parentheses. So G8 minus trunc G8, that calculation has to happen before we multiply by 60. And so now we get 12 degrees and then 17.2 minutes. All right, and again, let's compare this to our table. 12 degrees, 17.2 minutes. All right, we are cooking with gas. But that's a horrible decimal, so I need to do some rounding. All right, so let's go back into that formula. And this minutes, let's do some rounding. So I'm going to round, and I want to round this to one decimal place. Okay, so that's looking pretty good. Now, just for initial, showing off, if we do a little, I'm just going to fill down a little bit. But we've got 12, 17.2, 13, and 13.7. Let's take a look at the next couple lines. In fact, let me actually capture this in a little image, so I can, if I hit the right, I gotta hit the right buttons on my keyboard. All right, so just the first few rows, so I'll be able to bring them in, and so I don't have to keep flipping back and forth. So here's our spreadsheet. Come on. And we have 12, 17.2, 13, 13.7, 14, 10.2, and 15. Now this is 06.7, so we are going to have to do a little bit more formatting. But that's looking pretty good. I'm pretty happy with that. So let's change the formatting a little bit more. What we're going to do is we're going to we want it to have like a leading zero. So this 6.7, we want that to actually be a 06.7. And then so the way we do that is a text command. And we use text formatting. So it's all part of this rounding business. We're going to use the text command, text, and then the formatting is going to be 00.0. So what that means is, and I'm going to put that in quotes. What that means is I want to force it to have two decimals in front of, or two digits in front of the decimal place and one digit behind the decimal place. And I have to close that. Okay, so let's do another little fill down, and let's see if this 6.7 changes to a 0.6.7, and it does. Okay, so that's pretty good. We did some nice formatting there. Now we need to have the little d. Little d, again, this is basically the change in the elevation angle from one degree of declination to the next, because when you're on the open ocean, a degree is 60 miles. So hopefully you have better precision than 60 miles. So we definitely need to pay attention to the delta. And so and that's in what, cell H8. So we're going to take this and we're going to multiply it by 60 to get minutes, and then we're going to round it to one decimal place. So we'll say equals round, and that was what, an H8. So that's a decimal degree, but we're going to, the decimals of the degrees, we got to multiply by 60 to get minutes, and then we want to round this to one decimal place. All right. And again, I'm not going to do the autofill. Sorry, my kids are stomping around upstairs. Now, we're going to get this really interesting effect when we are sort of at the end of the table, because here it's literally subtracting blank space. So we're going to ignore that messiness there, but let's just compare it to our actual. Oh my goodness, my son's like stomping around literally right above my head. So we've got 56.5 is my delta, but one thing is we don't have the plus sign. All right, we don't have the plus sign. So we're gonna put in a plus sign, and we're gonna do that with a little logical structure. So if it's positive, we want to put a plus sign. All right, so what we're gonna do is we're gonna put in an if, what is it? If H8. If H8 is greater than, if H8 is greater than or equal to 0, so it's positive or a 0 value, then we want to add a plus sign. Otherwise, we don't want to add anything. And then we want to put a ampersand because we want to concatenate this with the next piece of text. Okay, and now it has added a plus sign. Okay, so I think the formatting is looking pretty good. All right, I think we're just about ready to go to the next step, which is to talk about azimuth. Now, azimuth is going to be very difficult. It's not that it's going to be very difficult; is that we have to actually derive another formula. Where's my little? I've got a little cheat sheet here. Okay. So for our azimuth, what I'm going to do is let's just go back to the drawing. I'm actually going to be solving for this angle T. Again, we're calling it LHA, but technically it's T. And so now what we now know is we now know the three sides of this triangle, right? We now know these three arcs of this spherical triangle. And instead, we were starting with LHA, but now we need to find Z. And Z is our azimuth, because again, if we are at if this is our zenith position, or if that's our assumed position, and we're measuring our latitude basically between the equator and the North Pole, going clockwise from due north is 0 degrees azimuth. Clockwise from that is our azimuth. All right, so this little angle right here is azimuth. Okay, so now what we need is we need to solve for that angle, and let's see if we can use the spherical law of sines. Spherical law of cosines. I'm sorry. And what I'm going to do is I'm just going to write the formula again, but I'm going to write it with slightly different letters. I'm going to put lowercase b at the start. So we're going to have cosine of b equals the cosine of a times cosine of c plus sine A sine C times the cosine of B. All right. So what we're going to do is we need to solve for that angle. And then once we've solved for that, then we're going to translate it into what we have in our spreadsheet. All right, so when you think about this, we need to first subtract this. So we're going to have cosine B minus cosine A cosine C. And then we're going to divide by, whoops, I went too far. We're going to divide by sine A sine C. So we're going to have cosine B minus cosine A cosine, supposed to say cosine C. And then we're going to divide by this, and then we're going to end up with cosine B. So we're going to divide this whole thing by sine A sine C. Sine A sine C. And that the whole thing equals cosine B. So how do you find B? Well, you take the inverse cosine. All right. So I'm going to kind of cheat a little bit. I'm going to just cross this out, and I'm just going to say cosine -1, and then we're going to say B. Cosine, inverse cosine, I should say, or arc cosine in terms of spreadsheets. So how are we going to relate this? We need lowercase a, b, and c. That's it. We don't need any angles. So lowercase a is CoAlt. All right, lowercase a is CoAlt, and then we actually have that saved in our spreadsheet as a name. No, I'm sorry. That's that was actually yeah, that was not named. So I'm just going to cross that out. That was actually in cell. CoAlt was in cell F8. This is F8. So this is F8. Now what's B from our original diagram? That was CoDec. Okay, and again, declination changes every line. So we're going to have to find CoDec, and that was in our spreadsheet. That was E8. CoDec was E8. So I'll do that in purple. So that was B. B, that was CoDec, or E8. All right, so we're going to have the cosine of E8 minus the cosine of F8 times the cosine. Now what was C? C was CoLat. Now CoLat, that was actually named. We named that in the top of the spreadsheet because latitude covers the entire spreadsheet. So C is CoLat. All right. All right. So hopefully this makes a little bit of sense. It's going to be kind of mind-numbing to type this into a spreadsheet, but basically, cosine of E8 minus cosine of F8 times cosine of CoLat, all divided by sine of F8 times sine of CoLat. And then we're going to have to take the inverse cosine of the whole thing. All right. So that's going to be our azimuth. Let's see if we can type this formula in. Now, because we want the azimuth to be in degrees, we're going to have to put the whole thing in degrees. So equals degrees. Now, just to make this thing a little bit easier, I'm going to actually do the nested parentheses for degrees just so it's a little easier to read. All right, and then we want the inverse cosine, so that's a cosine for arc cosine. What just happened here? I did not mean to do that. I hit the right button. So now what do we want? We now need the numerator. So I'm going to do another set of nested parentheses. The numerator divided by the denominator. So I'm trying to put these parentheses in here so that we don't get too lost. So the numerator was the cosine of E8. Remember that was CoDec. Cosine of E8 minus the cosine of F8. Again, F8 was CoAlt. And that's the product of that and cosine of CoLat. And we can actually just type in CoLat because that's a named item in our spreadsheet. Now, I want to make sure that whole numerator, I think I need to use another parentheses. Okay, so that's the whole numerator. And now we're going to divide by the denominator, which was the sine of F8. Again, F8 was CoAlt times the sine of CoLat. Okay, I think if I hit return, that gives us 120.87 degrees, and let's see how that compares to our 120.87 or 120.9 is on the actual table. So I think we did pretty well with that. Now, should I do some formatting? I think I'm going to do a little bit of formatting. Now this formatting, I'm just going to cheat, and I'm going to use the spreadsheet formatting tools to reduce the number of decimals, because we really don't need to do anything else with Azimuth. Besides that, I can then drag that down. We can see the different versions. Okay, so we have to add did we already add the plus sign to D? Yes, we did. What I want to do is I want to make this font size a little smaller, because the little d is slightly smaller. We're just going to do a little cosmetic things here, change our column sizes a little bit to make this thing a little bit more compact. And I think we could probably put that all the way over to the right. And I think I'm going to make all these things centered. All right, change the formatting of that and of D. All right, so little d, it turns out that little d, I do need to do that same thing about that text tool, because the D is going to possibly have not enough digits. So again, I'm just going to change this value to text formatting. And that's going to use the 00.0 format, so that it's guaranteed to have two digits before the decimal and 1 digit after the decimal. Okay, and so now I've already made the comparisons. So now what we're going to do is we're going to fill down. And we're going to go all the way to 91. And why don't we scroll down to the bottom of our table and see how we do at the bottom. All right, so let me, in fact, I think I'm done with comparing this one. I'm going to say don't save that. So let's scroll down to the bottom. Now again, this is not the page that Ruhif selected. This is 116. Ruhif selected 117. So that's a little bit more work to get there. But let's just take a snapshot of the bottom of this table just to see if our numbers come up. Okay. All right. So let's take a look at our numbers at the bottom of our table. Oops, I'm trying to move this thing over. So at 88 degrees azimuth, in fact, what I'm going to do is I'm just going to gray this line out. We'll just fill it in with gray, because we don't want that number. So at declination of 88, we have 68 degrees, 1.7 minutes. We have a little d of negative 29.9 and an azimuth of 4.5. Okay, that's really great. Okay, so that was the first part. Now, believe it or not, everything from here on out is going to be super easy. We're going to have a little bit of problem with some formatting, but everything's going to be super easy. So what I want to do now is I really hope to get this thing in under an hour. I'm just going to make a sort of a divider column here. And then what we're going to do is we're going to do the contrary table. So again, Ruhif had selected page 117, which again, it's local hour angle, 57 degrees, 67 degrees latitude. And we've got this strange thing where there's this line, and that's because the latitude is contrary to the declination. Let's go back to my original drawing. All right. My original drawing, if you take a look at the celestial sphere, the side view of the celestial sphere, and again, this is either a house or it's a ship. But basically, this area covers the entire page that we just did. The entire spreadsheet we just did. I'm sorry. The entire spreadsheet we just did covers this area. No, well, it does. It does cover this area for the body. Our Z value is here. So yes, this is 90 degrees of declination. So the body could have been anywhere along here. Okay. And it's basically either above our heads, or it's, high into the south or high into the north, above the north celestial pole. So basically we're in the northern hemisphere. The body is in the northern celestial hemisphere. And that covers the entire table we just made. However, what if the body is further south than the celestial equator? So this area in here, this is called contrary. So again, if our zenith is in the northern hemisphere and we have a body, that body has a negative declination, or that body is in actually the southern celestial hemisphere. So going back to our original celestial sphere diagram, if the body is down here, instead of subtracting from 90, we need to add to 90. I hope you can see that. If this is our body circled, if this is our body, and the celestial body, sun, moon, stars, we need to add that to 90. But it's going to be the same, essentially a very similar triangle, right? It's going to be the triangle's now going to look like this. The red segment's going to be the same. The green segment is going to, again, point towards the body. So, again, we'll be able to find our azimuth. We'll be able to find a lot of things. All right. So the thing about this drawing is that this is not 90 degrees. This is not 90 degrees of declination. It's only the small digits of declination up to the point where the body goes below the horizon, in which case, obviously, you're not going to sight something below the horizon. All right, so this is not going to cover the entire page. It's just going to cover the top part of the page. All right, so let's go back to our spreadsheet, and let's see how we can make this happen. So the first thing we want to do is we want to type in, this is going to be contrary. And I should make that same font as I made the other one. Now it's the same local hour angle, so I'm just going to copy this and I'm going to paste it. And the nice thing is that we used the absolute formula references. We used the $B, $2, absolute reference. Now here's the cool thing. We are going to literally copy this entire spreadsheet, because basically the formula is the same. We're going to make exactly one change. So I'm going to copy that whole section. I'm going to paste it, and now I just need to put in my declination. So I'm going to do a fill down, again, all the way to 91 degrees, because I need to get that differential, that lowercase d. And I can't do the differential unless I go down to 91 degrees. But so going back to my drawing, remember how this little piece right here, this was CoDec, or no, this was CoDec. This was DEC. So to find what we're going to call CoDec, it's not really CoDec anymore. It's extended deck, whatever. Instead of 90 minus the thing in question, we're going to do 90 plus the thing in question, plus the declination. So 90 plus the declination. Again, that's going to give us the degrees from the North Celestial Pole if our ship is in the northern hemisphere. All right, and again, we're not going to do autofill here. So that's literally the only change we're going to make, and let's see if it works. So let's go back to our table, and you know what? I really need to make these columns smaller so that we don't have to scroll so much. All right, so I'm just making the columns a little smaller, and we'll make some of these other columns disappear. Oh, you know what? I'm getting ahead of myself. So what we're going to be focused on is whether or not the first couple lines of our table are accurate. So and I'm not going to copy and paste it, but basically what we're looking for is 12 degrees, 17.2 minutes, a negative 56.5, 120.9 azimuth. And we see exactly that. We see exactly that. Okay, so I'm psyched. And that's it's almost done, but the problem with this column is if you look at the bottom of this column of the H sub C, we now have negative altitude values, which means that the body is 65 degrees below the horizon. So we're going to need to zero that stuff out. We're going to get to that in a little bit. But what we need to do is we need to copy this stuff again because we need to have the bottom half of the table. And this is going to get a little interesting. So I'm just copying that stuff again, and I'm just going to paste it over here. Now we need to make a different change. A different change. Now, just so you know, I think I didn't copy enough. I'm going to have to delete that. I was supposed to copy including declination. Let's try this again. So we're going to copy, and then we're going to paste. Okay, so we do want to start with declination. Now, just so I don't have a lot of scrolling left and right, I'm actually going to hide these columns because we don't really need to look at them anymore. So I'm going to say hide them. I can actually hide these columns. We don't need to look at them anymore. Okay. And let's take these columns and make them a little smaller. So right now, before I do anything, they're just these columns are just duplicating what they did. In fact, I'm just going to do a little fill down just so we don't have these crazy numbers. So right now, these are just duplicating. Oops, I forgot to increment my declination. Okay, so declination has to go between 0 and 91. Okay. And let's gray those out. Okay, so now what we're going to do is we're going to take a look at how we're going to change this. So right now, these cells in this spreadsheet is duplicating the first few cells that I did over on the left-hand side. In fact, you should see, like for example, declination of 4 degrees has 16 degrees, 3.1 minutes, 16 degrees, 3.1 minutes. So nothing has really changed. All right. So how are we going to change this to be contrary? And what exactly does contrary mean? So let's go back to my diagram. Let's go back to the celestial sphere. So right now, this section of the celestial sphere, this is what I'm going to call the left-hand pages. And then we're going to call these things same. Right? If we're in the northern hemisphere, all these stars are north of the celestial equator. That's the same designation. Over here, we did this section, which is called contrary. Right? So we have negative declination, so a southern declination, but a northern if we're in the northern hemisphere. So what we really need to do is work on this section over here on the far left. And if you think about it, if you go back to our hour angle, so this is our zenith. But like, what if we had the Big Dipper? I don't know. How can I draw the Big Dipper? What color can I use for the Big Dipper? So here's the Big Dipper, and it's pointing to Polaris, right? Well, if you see the Big Dipper and the Big Dipper is pointing up, meaning the Big Dipper can hold water, that is actually further. It's on the other side of the celestial sphere than we are. Like here's our zenith. That is on the other side of the celestial sphere. So think about what the hour angle is. The local hour angle is going to be all the way over here. It's going to be closer to 180 than it is to 0. Okay? So the local hour angle, we need to be talking about the other side of the celestial sphere, but also north of the equator. So we're gonna talk about, it's basically the math is going to be the same as quote unquote same, but we need to change our local hour angle for the table. All right. So to do that, and let me just check my, because I've been going sort of on autopilot. So I make exactly one change. I filled that down because I've got a little bit of a cheat sheet going on here. So now we have to change our LHA. All right, we have to change our LHA. And so we're going to do below the HC column of the third set, where is H sub C? So S. So this place right here, I guess it's S100. We are going to calculate a new LHA. All right, so we're going to do equals, and then we're going to put in the, just a little announcement, LHA, colon, space, and then we'll do an ampersand. All right, now we want to change this to the other side of the celestial sphere. So we're going to be doing 180 degrees minus our original LHA, which was over at cell B2. I'm not going to type in LHA because LHA was in degree, or was in radians. So I'm going to type in B2 because that was the original LHA. Another ampersand. And we want a comma, space, and then we want to have either 180 minus or 180 plus. Again, we're going to be on the other side, but then there's actually going to be two symmetric triangles. So 180 plus B2. All right. And I think that is going to be, all right. And we're going to make that nice and big. We'll do that in 18-point font. We're also going to write the word same. Also in 18-point font. All right. So I think I'm going to go overtime with this, but I hope this this exercise, this demonstration is entertaining for for some folks, possibly people who are retired and don't have to go to their job in the morning. Anyway, so we've got a new LHA, but now the bad news is we have to actually convert this thing to radians. So how about cell? We'll call this V100, where we have to have the LHA in radians. So we're going to do equals radians, and we're going to do 180 minus B2. So again, B2 was the original LHA that we had typed into the very, very top of the spreadsheet. Now, so this thing can be useful. Why don't we name this cell LHA bottom? LHA bottom. Okay. So now we're going to go back up to our formulas. Now let's take a look. Where was the LHA actually used? It wasn't used in H sub C. It wasn't used in D. It was not used in Z. It wasn't used in CoDec. It was used in CoAlt. It was used in CoAlt. All right. So all I have to do is just, I literally have to type in the word bottom, LHA bottom. And now that's going to change this entire spreadsheet. So I think I'm ready to fill down. And I think the second half, or the third half, the third of this spreadsheet is complete. Now, the bad news is that we are getting H sub C values that are negative. All right. And so you're not allowed to have elevation angles that are negative. Now, I just want to show you real quick by changing these cells so we can actually resize these. So let's actually scroll through this entire part of the spreadsheet, and we can get rid of these things. We can hide them, and we can get rid of column Z. We don't need it. Okay. So if I scroll down, I see these values are all positive up till declination 14. Then up to declination 13, and then it turns negative. These values are all negative, and then they turn positive at declination 14. Oh, you know what? I completely forgot to check to see if our values were correct. So let's do declination 14, and let's compare it. So we have 0 degrees, 55.7, and then we have 54.5 azimuth, and that's exactly what they've got as well. All right, so we're doing pretty well. But now what we need to do is we need to combine these two columns into one. And the thing is, I really tried thinking hard about how I could simulate that line and put them both in the same column like they are in the table. And I just decided that was too much work. But now that we know that our values are pretty good, let's collapse this stuff back down so I can do fill down more easily. Let's collapse this back down. and then let's see how we can change these so that we only have one column, on the contrary side. We only have contrary over here on the left, and we only have same over here on the right. So how are we going to do that? Well, what we're going to need to do is we're going to need to add a sort of a conditional. We need to add a conditional, and remember that this was all based on P8, the value in P8. Which P8 is now hidden, but basically P8 was the decimal version of this. And we need to ask ourselves, if the decimal version is negative, don't show this value at all. Okay? So what we're going to do is we're literally going to go in front of this entire thing, and we're going to make an if statement. If, and then we're going to do $P8. If $P8, the reason why I'm using the $ is because I want to be able to copy this formula multiple times. If $P8 is greater than or equal to 0, then I want it to show this whole thing, truncate, blah, blah, blah. Otherwise, I want it to show just sort of a dash. I'm good. I'm just going to use equal signs. Okay. Now, nothing much happened, but let's fill this thing down and let's see if it changes the negative values to dashes, and it did. Now I'm going to cheat just simply for the sake of time. I'm going to cheat, and I'm just going to literally copy and paste the segment, this little if part. I'm going to just copy that, and I'm going to paste it into the next bunch of cells, the next 5 cells. And it's going to break my formulas, but that's okay. I'm going to come back and I'm going to fix them. I'm going to say copy. All right, so I'm just going to go in front of this if statement, and I'm going to insert that little bit. All right. Now what's happening is every time I hit enter, what it's going to do is it's going to close the parentheses for me. So it is smart enough to close parentheses, but I'm just pasting it all the way across, and this is it's going to break things a little bit. So I'm going to have to go back and replace it. But I'm just using this copy and paste just so I don't have to tediously type that every single time. Okay, now I need to add this part at the very end. All right, I'm going to copy that. Now, unfortunately, they already added a parentheses, so I'm going to delete the parentheses and then paste what I need to paste. So I'm going to delete one parentheses, paste what I need to paste, and I'm just going to do that 3 more times. Delete a parentheses, paste, and delete this parentheses, paste. It is nice that it does fix the formula. If you don't close your last parentheses, it will close it for you for a formula. Now the problem is that now I've hard-coded this if statement is using P8. But over here on these last 3 columns, the if statement needs to be relative to x8. So I just need to change the letter P to the letter X. And notice that these are now starting to turn into dashes. All right, because in cell X8 is the cell that I'm really interested in, whether it's positive or negative. Okay, so now that those changed to dashes like we wanted, and now we're going to fill down completely. And that looks pretty good. Now we no longer need cell or row 99 to be visible, so I'm going to just hide that. I do need to have it be still there. I'm just going to hide that row. And we can now resize all these rows so that we can actually see our final spreadsheet. Okay. So I'm going to go back and I'm going to take a photo of this. So let me take a little snapshot. I just want to do the snapshot of sort of the crossover, where the top half is contrary and then the bottom half is same. So let's compare this to our spreadsheet. I'm just trying to come on. Trying to get this. Oh, I can't change the size. All right. So how did we do? So with a declination of 11 degrees, we have 1 degree 54.4 That's correct. We have a little d of negative 56.7, azimuth of 124.5. That's pretty good. How about under same, let's go down to azimuth of 17 degrees. Azimuth of 17 degrees. How'd we do? 3 degrees, 45.7 minutes. A little d of 56, a positive 56.7, and an azimuth of 53.5. Okay. Well, that is it. So we've got basically, I've tried to duplicate this page that Ruhif had selected, but I ended up duplicating two pages. Now, here's the cool thing about the spreadsheet is that you could type in any latitude and you can type in any local hour angle. So you don't need to carry around those big heavy books. If you wanted this spreadsheet will duplicate literally every page of those tables. All right. So again, I want to say thank you very much to Andy Howe for his excellent work at the nav station. And I think I am signing off. Oh, I will share the spreadsheet. So I'll put a link in the description, but it won't be there this minute because I want to clean things up a little bit. But I will share that spreadsheet. Link will be in the description. All right. So going back to my timer, it's now 67 minutes. So hour and 7 minutes, not bad. I should have talked less. All right. I hope you guys have a great rest of your day. Bye-bye.